welcome everybody to a new semester and a new series of the Heidelberg Joint Astronomical Colloquium. Thanks to all of you here who have made the trip down from the hill. And I think we are in for a very exciting program on here. We're going to be going over very many areas of astrophysics, ranging from high energy, low energy, nearby, distant. And I wish everybody a great deal of fun and interest in the coming weeks. Now, the first colloquium today is by a guest from the USA, and I'm going to hand over to Ralph Klesson to make that introduction. Maybe you want to say a little bit about the structure.
Okay, welcome also from my side. And before we get to the speaker, let me also announce that the akademische Mittagspause, so the academic lunch break, is given this semester by the Structures Excellence Cluster. So for those of you who are not familiar with this format, it's actually super cool. It is a 15-minute talk in the center of the old city for the public in the Peterskirche, followed by another 10 to 15 minutes of discussions. It started yesterday and it will continue every working day throughout the end of the semester. Typically on Monday, when it's not a vacation day, there will be music and there will be discussions about structure in the music of Bach and Debussy and Ravel next to structures in the natural world. So everyone is welcome. And as I said, it has just started and it is open to everyone. With that, let me introduce today's speaker, Karin Sandstrom. She is from the University of California at San Diego, but in the end, she may be well known to many of you because she did her postdoc position first as a regular postdoc and then with a prestigious Marie Curie Fellowship up the hill at the Max Planck Institute for Astronomy. She came there from a bachelor in Harvard and a master and PhD in Berkeley, so on the other side of the US. And after finishing here in 2000, now I need to see, 2013, she moved with the Bart Bock Fellowship to the University of Arizona in Tucson. And from the desert in 2015, she went back to the West Coast, but to the southernmost part, almost to the University of San Diego, which she has been ever since. And, well, that is a big word, in the last 8 years. She has done many interesting observational things. I would say currently the most exciting one is looking at galaxies and the emission of dust with the James Webb Space Telescope. And this is what we will be learning about today. But I guess if I ask you what is the one you're most proud of, it's probably the managing that there is now a separate astronomy department at the University of California in San Diego. So there was a split between physics and astronomy, and it worked very well. Back to astronomy and to fantastic images and science that can be done with the Hubble Space Telescope and James Webb, of course.
Well, thank you very much. It's really nice to be back. And this is true. We now have a Department of Astronomy and Astrophysics at UC San Diego. So anyone out there who's considering places for a PhD or places for a postdoc or places for a faculty job, just know that that exists. So I'm very excited today to talk to you about early science from the Treasury program we did as part of the PHANGS survey. And initially, when I got signed up for this talk, there was a mention of wanting to have potentially a local speaker for the first one. And I think maybe this sort of counts because much of the work that I'm going to show you is the effort of people who are either in Heidelberg now or have been in Heidelberg at some point. So many of the papers that we're going to talk about are really, very local product. So And just to emphasize that, I want to start off by thanking a few people who have been involved in this. So for the JWST survey, the PI is Janice Lee, and we have several co-PIs, Kristen Larson, Adam Leroy, myself, Ava Schinner, and Dave Thilker. And we had a lot of leadership of the team from Eric Roslowski. The early science data reduction was led by Oleg, who's up there, and Tom Williams, who's now at Oxford, but was a postdoc here in Heidelberg. The leads of the early science papers I'm going to mention are listed here. The red people are postdocs, and the blue are students, although I'm told this now needs a reclassification, so congratulations to Dr. Kim. I don't know if she's here. And lastly, a lot of the beautiful images I'm going to show you are the work of Judy Schmidt, who does just amazing visualization of JWST observations. So the FANGS team, you may know, is a very large collaboration now that involves a lot of people around Heidelberg. It's led by Ava Schinner, and I think a number of people in the audience are members of FANGS. So thank you all for all the amazing effort. So to start, as you may know, on Christmas 2021, the James Webb Space Telescope was launched. This is now the largest telescope that's in space, 6.5 meter mirror. And the delightful news is that they project that this will have something like a 20-year lifetime. So that's really amazing. And after you've seen, I hope you've already seen a number of the amazing things that this telescope has enabled already, not even in the first year of its science operations. But imagining 20 years of this, I think, is truly outstanding. So for the purposes of what I'm going to talk about, I want to focus on, what JWST lets us look at with its extremely high angular resolution and incredible sensitivity over the near to mid-infrared. And my talk is going to be focused on, observations related to star formation in nearby galaxies. And the near to mid-infrared is really extremely rich with information about star formation and the interstellar medium. So this includes starlight continuum. This you can see dropping off at the shortest wavelengths. It includes rotational and vibrational lines from molecular hydrogen. It includes the series of recombination lines from hydrogen. And in fact, in the mid and near infrared, those are basically unobscured in most conditions, so we don't have to worry about dust as much. There's also the dust itself, showing up as continuum emission, and then vibrational features that come from polycyclic aromatic hydrocarbons. And this is all extremely informative about the star formation that's occurring, about the characteristics of the ISM. So the near and mid-infrared are really important because of two things in this, to summarize. We can see through the dust because the attenuation is very low in the near and mid-infrared. But the dust is also re-emitting the light it's absorbed at those wavelengths. So we capture that re-radiated light as well. So just to give a slightly more background on these features right here, because that is my ultimate favorite thing and should be everyone's favorite thing with JWST now, right? These are features coming from polycyclic aromatic hydrocarbons. And I say this, pause, in the chemical sense is a very much more strict definition than what's typically used to refer to, kind of hydrocarbon molecules in an astronomical sense. But these are basically structures of carbon with hydrogen attached. And after they absorb a UV or optical photon, they vibrate and de-excite and produce these particular vibrational features that we see ubiquitously in the mid-infrared and near-infrared. I want to give you a little bit of an overview of JWST's capabilities and kind of emphasize why this is so revolutionary for looking at nearby galaxies. So to start, here is a summary of the JWST instruments. So I'm going to be focusing on imaging capabilities, but I hope someday in the future to tell you more about spectroscopy capabilities. But the talk will focus in particular on imaging with NIRCam and MIRI, which are the two kind of workhorse imaging instruments on the telescope. And they cover, NIRCam covers up to about 5 microns, and then MIRI takes over and covers out to around 25. So in those wavelength regions, there's a number of filters. And for the observations I'm going to present, we covered the 200 wide filter and then a set of medium band filters around 3 microns. And this filter is primarily going to be tracing starlight. So we'll see the near infrared emission from the populations of stars. And these filters are chosen to bracket a PA feature at 3.3 microns, which you can see here. And the hope is that using these 2 bracketing filters, we can get a clean subtraction of all of the continuum and look just at this PA feature. But in addition, these also are tracing starlight. And then this one includes some interesting emission from potentially other types of PA molecules. In the mid-infrared, we cover 4 different filters. You can see those highlighted here. And these are chosen to sample primarily PA emission at 770 and 1130. So this is 7.7 and 11.3 microns. And then potentially dust continuum. So this is from hot grains that emit at around 21 microns and longer wavelengths. And then the 10 micron feature or 10 micron filter may trace continuum in some cases. In others, it may be sensitive to silicate absorption. In others, it may be tracing mostly PA emission still. So this is a filter that's useful for many purposes. And here is a here's a illustration of those filters shown on top of the spectrum for PA emission. So you can see this 7.7 feature primarily being traced by the 770 and then 11.3 here. So in addition to this amazing wavelength coverage and imaging capabilities, one of the truly unique things we have with a 6.5 meter telescope is very high angular resolution. This is the resolution full width half max of the telescope as a function of wavelength. And this is in the NIRCam filter, so the near infrared. And just to highlight, here is what you could previously do with Hubble with a 2.4 meter mirror, which is amazing, wonderful, amazing telescope that just turned 33, I think today or yesterday. But JWST, you just get a much higher resolution at that same wavelength. And then the comparison to Spitzer, even more dramatic. So here's the mid-infrared PSF ranging from like 0.2 arc seconds up to around 0.8. But at the same wavelength, Spitzer would be way up here. So the improvement we get in resolution for these images is really incredible. And to give you an idea of what that means, here are a few scales that you may probe in nearby galaxies. So for instance, in a very nearby galaxy, the Large Magellanic Cloud, or in a 10 megaparsec distant galaxy like M51, at the longest MIRI filter we cover, that resolution corresponds to 30-ish parsecs in M51. And just for comparison, here is the Orion Molecular Cloud Complex with a scale bar showing that size. So even in M51, we have the resolution to separate, the different components of something like the Orion Molecular Cloud. So this is very high resolution. So that brings me to the PHANGS survey, which has been in the process of studying star formation at very high resolution in nearby galaxies. So this stands for Physics at High Angular Resolution in Nearby Galaxies. And this is a large project led by Eva Schinnerer. The project scientist is Adam Leroy, team manager Eric Roslowski, and there are a few main surveys that have been a part of PHANGS. That includes ALMA, led by Adam Leroy, MUSE, led by Eric Emselen, and HST and now JWST, there's JWST, led by Janice Lee. So the goal of PHANGS is to understand the big picture of the baryon cycle in galaxies. So how stars form and how the clouds that give rise to those stars condense out of the diffuse interstellar medium, how those are then revealed and their energy through feedback is put back into the interstellar medium. So this cycle is at the core of galaxy evolution. right? Driving the buildup of stellar mass over time, the energetics of the ISM, the distribution of metals, the enrichment of heavy elements. And at its core, it depends on two scales, sort of. So there's the scale of individual star-forming units, clouds, clusters, H2 regions. These are quite small in galaxies, on the order of hundreds or smaller parsec scales. The properties of those regions, though, are greatly influenced and set by the context of the whole galaxy. So the distribution of gas throughout the galaxy, its properties, the dynamics, all kinds of large-scale characteristics. So to fully understand how these individual star-forming units connect to the big picture, you have to observe with multiple scales. So something that's both high resolution, that gets you those objects, and then wide field, so you see the full context of the properties of the galaxy. In addition, you need multi-wavelength data because these different stages occur and are traced by widely different wavelengths. So to follow the transition of the gas from its atomic phase into its molecular phase, we trace the properties of these molecular clouds with CO using ALMA. The star formation itself, when it's not deeply embedded and is revealed, we can see using ionized gas tracers like H-alpha and the UV emission from young stars, UV and optical emission. So that part of the cycle is traced by HST and MUSE observations. But what's missing and what JWST is getting us is this phase where star formation may be deeply embedded in the clouds where stars are forming. So these are very dusty, and a lot of the light from these young stars is going to be absorbed by that cloud, re-radiated into the infrared. So to truly kind of capture this whole cycle, what we need is infrared emission. So let me tell you a little bit more about the PHANGS sample to give some context for what we're going to look at. PHANGS is a sample based on a selection that picks out galaxies that are close, not edge-on, and visible to ALMA. So this is meant to sample the full span of the star-forming galaxy population at Z of 0. So you can see the targets of the ALMA survey overlaid on the kind of overall galaxy population here. So these, there have been around 90 galaxies that have been observed with ALMA, getting maps at around an arcsecond resolution in CO, carbon monoxide, which traces the molecular gas. You can see a few of the galaxies here. All of the data, by the way, is publicly available if you're interested in this, and can be found at the large program website for ALMA. So this was the starting basis, getting the ALMA observations here, and a subset of the galaxies have detailed information now at optical wavelengths, both with MUSE. So that's shown here. This was led by Eric Emselem. And what you see in the images here are actually taking the data cube from MUSE, which is an integral field spectrograph. So you have a spectrum at every pixel covering the part of the optical wavelengths, and collapsing this to show basically all of the ionized gas nebula and the starlight in these galaxies in this beautiful image. So there are around 20 galaxies with the MUSE data, and there's a number of products that are publicly available, including all of the reduced data and a catalog of nebular regions, which you can find publicly available as well if you're interested in that. There's also around 38 of these galaxies that have been observed with HST, and this was a Cycle 26 Treasury program led by Janice Lee. And from that, there are catalogs of stellar associations and clusters. And this will be a key part of keeping track of where all of the star formation is happening. These are the unobscured, basically, portion of the star cluster population. So just because I can't summarize too much of PHANGS in this one talk, and I want to get to the JWST data, let me just give you a quick overview. There's a lot of papers that have come out of PHANGS and many key results, but maybe to just summarize briefly, with around 100,000 molecular clouds, around 20,000 H2 regions, and another 100,000 stellar clusters and associations, what we can see is that the properties of molecular clouds vary, and they're shaped by the environment within their host galaxy. Feedback is happening very quickly. So when stars form, there's feedback that very rapidly disperses molecular clouds. And the star formation process is quite inefficient. So not very much of the actual molecular cloud in the end is being converted to stars. So there's many other exciting results here, particularly on ionized gas, metallicity, star clusters, dense gas, many things. But I'm going to move on now to talk about JWST. And what I just want to mention before we do that is that a lot of these questions rely on tracing star formation, and the infrared is critical here. So what we may be missing when we think about our assessment of star formation is the deeply embedded clusters, the youngest ones that are still in their parent molecular clouds and have not yet emerged to be visible easily in the optical. We also may be missing the earliest phases of feedback. So whatever process, radiative feedback, mechanical feedback from winds, various things that may disrupt the parent cloud, this is a very important question to understand this full baryon cycle. In addition, star formation tracers without some information from the infrared have a number of uncertainties, key uncertainties that we'd like to overcome when we have matched resolution infrared tracers that let us see this deeply embedded star formation. And in addition, we have little access to dust as a tracer of the ISM, and there is a lot to be learned there, which I will get to at the end. So this motivated a Cycle 1 Treasury program where we observed 19 galaxies in 8 bands with MIRI and NIRCam. Here's an illustration of various star clusters at different levels of extinction, up to AV of 30, and the different filters we observe with JWST and MIRI. So just for reference, at signal to noise of 10, we expect to detect a 2,000 solar mass cluster with AV of 10. So this is a very complete assessment of where star clusters are. In addition, we expect to reach a signal to noise on the diffuse interstellar emission, which lets us trace kind of the typical gas surface density within a galaxy's disk. And you will see that shortly this was accomplished. So as an illustration of what the resolution here is, this is the previous best image of NGC 628 in the infrared at 8 microns with Spitzer, which is already quite beautiful. But I know you've already seen what this looks like with JWST because I showed it on the first slide. But here is the comparison with approximately the same wavelength with JWST. So this really is an incredible jump in resolution. It lets us see a huge number of very interesting features, bubbles, filaments, star clusters, all kinds of things. So over the next little bit, we're going to explore that. So just to highlight, JWST imaging gives us a higher physical resolution than Spitzer did for M33 in the local group, out to a distance of 16 megaparsecs. So this really opens up a huge number of other galaxies for studying the interstellar medium and star formation in that level of detail. Our sample is composed of 19 galaxies, all of which have ALMA, HST, and MUSE observations. So this is kind of the full data set from PHANGS brought to bear on these 19 targets. The key science goals are the following. So the first thing, I'm going to find all of the clusters. So where even the deeply embedded ones, the ones that you would miss with HST because they are behind too much dust. We'd like to see all the embedded star formation. So test out if there is a reservoir of molecular gas without any star formation, or if this was just a lack of being able to see, where the deeply embedded things were. We'd like to try to measure some timescales of feedback, and this is something you can do with the statistics of how many clusters and clouds and H2 regions exist in different phases of their evolution. We'd also like to map the characteristics of dust, and in particular the PHA emission, and test out how star formation prescriptions can be updated having this information from the infrared. The first 4 galaxies we observed are shown here, and these observations were done in July and August of 2022, and they are the subject of a set of early release science letters that came out in February. So I'm going to focus on these 4, but we are in the midst now of looking at, around 16 others or 15 others. And the first 4 galaxies actually span a pretty interesting range of properties. So there's a low mass, lower metallicity dwarf. There's a beautiful grand design spiral, NGC 628, moderate mass. I can never remember the M number for 628. Does anyone? It's a Messier object, but 74. Thank you. In case anyone's more familiar with that. Then we have NGC 7496, which has got a beautiful bar and an AGN in the center, and 1365, which is a massive starburst, circumnuclear starburst, bar-driven starburst, and this is the highest mass galaxy in this first set of 4. So I just want to show you some of the data to start. So here is NGC 7496, and I think, for those watching on Zoom probably have the best view. These are really incredible images. So this is the one that has AGN in the nucleus. You can see the very bright point source with some of the diffraction spikes. Here is the same galaxy now combined with HST. We move on to IC 5332. This one is much more dwarf-like, not quite a dwarf, but it's still very flocculent, and it has much more kind of disorganized spiral pattern just from the appearance here. Here is 1365, which has this incredible starburst in the center. And while you can see some of these are diffraction spikes from bright point sources, there actually is evidence that there's some kind of outflow coming from this central starburst by the kind of spray of interstellar medium features pointing away from that region. And it's very bright at 24 microns, which is why it shows up as so red in this particular image. So lastly is NGC 628, which I think you've probably seen because it's been a press release image. It's very incredibly beautiful image, and it just has this kind of amazing kind of almost fractal-ish kind of thing where you look at it and you see more and more detail, and you look in more finer regions and see more detail. So we'll do that briefly here. To start, very interesting region in the center where there's kind of a hole in the distribution of the ISM. We'll come back to that. But we can zoom in on this, which is a dramatic bubble blown in the ISM called the phantom void. We'll hear more about that as well. We can go up here and start to see, lots of filaments and interesting bubble features throughout the ISM. The screen is maybe slightly saturated, so you can't quite see all the detail here. Moving along, we have lovely filamentary structures throughout the ISM tracing the spiral arms, lots of interesting star forming regions showing up on the edges of bubbles, that sort of thing. And here's just a good moment to look at this beautiful galaxy. So what I'd like to do now is give you a little tour of what we learned already from these images. And the results of this are published in a volume of AppJ letters. You can find it here, just Bang's first results, AppJ letters. We have progress in all the key science areas of the proposal. So I'm going to show you kind of a bunch of results. Sorry for the whirlwind tour, but they're all so exciting and I can never decide which things to cut. So we'll start by looking at the question of where are the clusters? Are there lots of embedded clusters? And we'll begin by zooming in on a region of the spiral arm here of NGC 7496. So this is a paper led by Jimena Rodriguez, who's a postdoc at the University of Arizona. And what she did, and again, it's a little bit stretched, so can't quite see the detail on the screen, but these apertures circle various sorts of clusters. And what you're seeing are different HST bands into the near UV right now. So all of the red ones and the yellow ones that circle the red ones are locations where there are embedded clusters that we don't see very well at all in HST, but in JWST, they show up quite well. So here we're going at 2 microns, 3 microns, 3.3 around that PA feature, and 3.6. And you see in all of these spots, there is some object at that location. And in particular, they're very easily noticeable in a lot of cases at 3.3 microns, which is tracing this feature, this PA emission feature. So this is dust in the ISM that's heated by the star cluster. And it is our highest resolution tracer we have of the interstellar medium because it's the shortest wavelength PA feature. So we can even go to longer wavelengths and you see that these clusters are now very bright, even out to 21 microns. So putting this all together, these candidate embedded clusters turned out to live in this portion of the color space or color magnitude space. And after measuring their ages with SED fitting, everything that ended up there was young. So these clusters, all of them are young. 6 of them are in fact less than 1 million years old. And there's 67 embedded cluster candidates that were found in this whole galaxy. So this has the possibility to even double the number of clusters that were in this galaxy at less than 2 mega years old. So this is potentially an important step in characterizing all of the star formation that's happening. So moving on to another very exciting galaxy, NGC 1365 with its starburst. Here again, the near infrared and mid-infrared view of this galaxy was able to identify a lot of candidate embedded clusters. So here you have a zoom in of this central starburst region. Everything circled in red are newly identified clusters with JWST imaging. And there's around 16 of those. These are all actually massive young clusters. So masses greater than 10 to the 6 solar masses and ages less than 10 million years. So in this big starburst, you have a large population of massive clusters that are being formed, and they are revealed in the mid and near infrared. So with the statistics of how many clusters you can detect, either only with JWST or with HST, you can work out an estimate of what the embedded phase of their life, what the lifetime is of that. And that turns out to be something like 1.3 million years from these statistics. And we'll see other numbers from completely different techniques of estimating that timescale that agree quite well in other galaxies coming up, which is very interesting. So this galaxy center is the subject of a lot of interest because it has this huge starburst, which is driven by gas flowing in along the bars. And this was investigated in detail by Ava Schinner and Eric Emselem, looking at where the clusters fall on these different parts of this circumnuclear region. And one thing they found is that having identified basically all of the embedded star clusters to some degree, the distribution of star formation is lopsided. So you see many more clusters up in this northern arm than down here in the south. And this is something that occurs in simulations occasionally. There's a transient lopsidedness. Things are not always perfectly symmetric. And the timescale here, suggests that this feature may not be around for a long time, but that at this moment, there's just more star formation occurring in this region. So this is interesting from the perspective of thinking about our own circumnuclear region in the Milky Way, where the lack of star formation in various clouds or the abundance of star formation in other clouds is, puzzled over quite a bit. So, showing this kind of situation occurring potentially in other circumnuclear regions as well is very interesting. In addition, Daizhong Liu, who's a postdoc at MPE in Garching, looked at the properties of the gas subject to feedback from all of these young clusters and was able to show that the dissociation of CO, molecular CO into C1, is actually enhanced in this region of the starburst as well. So it seems like the feedback from these young stars that are forming in all of these regions is starting to dissociate some of that gas. So I want to move on to a very different cluster, and that's the nuclear star cluster in NGC 628. And this was a paper by Nils Hoyer, who's a a grad student in IMPRIS up at MPIA, who works with Nadine Neumeier. Nils looked at the nature of the nuclear star cluster, which I'm not sure why it looks quite so stretched here, but you can actually see very nicely in the center, there's a compact nuclear star cluster in this galaxy. And with that data plus Hubble observations, he was able to fit the SED of this nuclear star cluster and work out that its mass is around 10 to the 7 solar masses with an age of around 8 gigayears. And there's been essentially 0 star formation over the last few gigayears. And interestingly, it sits kind of in this void where there's no gas in the center. Doesn't show up in CO, it doesn't show up in the tracers we have from JWST. So in fact, if you look back here, the reason this looks so blue is that we're seeing the starlight only, essentially. So the way that this 3-color image is put together is that things would look blue if they have a decreasing SED as a function of wavelength. So this is really an old stellar population, and the question is, how do you maintain this void, or how do you prevent gas from getting to this cluster and forming stars over that long a period of time? So don't have an answer for that, but something has prevented star formation. It could be dynamics prohibiting inflow, or it could be gas that's been cleared out by some kind of other feedback process. So going back again to beautiful NGC 628, the other thing you might immediately notice when you look at this is all of the filamentary structure throughout this galaxy. And that was something that I think people, really honed in on right from the start, because it's so beautiful. And there's a number of approaches to figuring out the nature of those filaments. So you can search for them in an automated way. And here is the result of one of those. So we had a couple of early science papers trying to investigate the nature and properties of these filaments. And one of them used both the combination of HST, showing the dark dust lanes, and JWST, showing them glowing brightly, that same dust, and compared the two. So this is a paper by Dave Thilker. And what you see here is kind of the inverse of the HST image. So you can see all of this dark dust lane showing up. Comparing that then to the JWST, where you can see the same filaments, just very bright in emission. Dave worked out that in 40% of the time, these overlap very nicely. So they're tracing the same thing. And you can basically work out a joint kind of network of filaments between what you identify with JWST and with HST. And kind of the interesting thing is that around 50% of the mid-infrared is coming from what you would identify as filaments. And if you look in detail, around 75% of the H2 regions and 60% of the young clusters are also located within the boundaries of those filaments. So this is suggesting something about the overall organization of the ISM in these galaxies and where it forms stars. And then to build on that, Sharon Might looked into what can describe the spacing between the filaments. And you might think of this in terms of the tomb ray length, which would be a length that's stabilized by rotation in the disk. You may think of this in terms of the gene's length or the scale height, various relevant characteristic lengths that might be related to the filament spacing. And what Sharon found is that the actual filament spacing in these galaxies most closely matches the turbulent gene's length. And so this may be the thing that's relevant here for setting kind of the scale at which these dense structures collapse. So very exciting. I know this is a whirlwind tour. We're about halfway done. Hope everyone's okay. So moving on to the next thing. In addition to the filaments, some of these you may identify actually as spurs, so things extending into the interarm region. And there's been quite a bit of debate over the years about how star formation occurs within spurs, or if it's primarily in the spiral arm and then just kind of drifts along with the spur. So Tom Williams, who is a postdoc here at MPIA for up until like June maybe, or recently, looked at 2 spurs in NGC 628 and found that given the pattern speed that's known for this galaxy, the star formation has to have occurred within the spur. It's not just the leftover of, when the spiral arm passed by, because the time scale for the tracer of these star formation episodes is much shorter than the actual time that has passed since the spiral arm passage. So this is showing that, we can identify regions of star formation associated with these features in NGC 628. So in addition to filaments, the thing you always also notice first about this galaxy, I don't know, anyone probably knows what I'm going to say next, bubbles, lots of bubbles, tons and tons of bubbles. This is the largest one in NGC 628 at least, and they are everywhere, loads of bubbles. So this was kind of the dramatic first impression when you see this data. You're like, wow, it's full of bubbles. And so we had a couple of efforts to characterize these bubbles and understand, their properties. So one of those was looking in particular at this very large bubble, which is the phantom void. And this was by Ashley Barnes, who's a postdoc at Bonn. And Ash did a number of measurements related to this bubble, including figuring out that to maintain its circularity versus the differential rotation of the galaxy at this scale, it has to be expanding at a rapid rate, so somewhere between 15 to 50 kilometers per second. And this matches up with what you see actually if you try to measure some expansion from the local velocity field in CO. In addition, this bubble seems to be driving star formation all along its edge. And this turns out to be quite significantly seen if you look at the age of different clusters. So this is the age of stellar associations, not clusters, sorry, as a function of radius from the center of the bubble. And you can see that they are piled up along the basically edge of this shell with nothing very young in the center. Originally, there are some clusters in the center that probably were the starting point to drive the expansion of this bubble, but the current star formation activity is around the edge. So I'm not going to say too much more about bubbles because you have an RE colloquium, which everyone can attend on May 25th by Elizabeth Watkins, who's a postdoc at RE, who has done a ton of the work in actually finding bubbles in NGC 628. She found 1,700 of them by visual inspection, which was a lot of work. And it's also a foundational data set to try to drive like automated ways you might, do this in the future, not having to have Liz individually look at every single galaxy and by hand identify bubbles, because that's a lot of work. So I definitely recommend you go to her talk to hear more about this on May 25th. So in the last bit, we'll talk briefly about star formation again and the timescales of star formation, and then pause at the end. So zooming in again on NGC 7496, you can identify a number of compact sources in the infrared at the longest wavelengths, so 21 microns. This was done by Hamid Hassani, who's a graduate student at University of Alberta. And he classified all of these 12,000, 13,000, or 1,300, sorry, compact sources by hand and figured out color cuts that give you ISM sources and not background galaxies, not stars, that sort of thing. And it turns out that of these compact sources he identified, 92% of them are associated with H2 regions. Here's their luminosity in H alpha. And they are associated with masses of 100 to 10 to the 4 solar masses of a newly formed stellar population. So less than 10% of these are faint in H alpha. So what this suggests, again, is that the embedded phase is short. There's not very many of these that are so deeply embedded that they have no signature in H alpha. So this is another constraint on that lifetime of embedded star formation. Another way to approach this is through the statistics of populations of star clusters and H2 regions and molecular clouds. And this is work led by Jaeyeon Kim, who I understand is now Dr. Kim, got her PhD this week, like yesterday maybe, or the day before. So congratulations. I don't know if she's around. And in collaboration with Melanie Chavance, who's her supervisor. So what they did is use the statistics of the clouds you identify in CO, H2 regions, and H alpha, and now mid-infrared to reveal the timescales of these various phases of the life of a star forming region. And this is something really, it's called the tuning fork principle. This was explored by Diedrich Kreutzen and Stephen Longmore in 2014. And Jaeyeon has done a lot of work as well as Melanie in developing this and applying it to galaxies and FANGs. So what she found is that there is only, again, a small phase where you have infrared emission, but not yet H alpha. And this is something like 2 megayears of time where you can have a deeply embedded phase of the star formation. So now I think actually that's like 3 different techniques, which is kind of cool, all giving something around 1 to 2 megayears for some phase of this that's quite deeply embedded. So that's actually quite different approaches as well to measuring the life, the duration of that phase. All right, so on to the last topic. And I know this is a like fire hose of information, but I hope it's giving you an idea of all of the exciting stuff that's possible with JWST and nearby galaxies. The last thing I want to talk about is pause, and this is my favorite topic. Pause are everywhere, and in fact, essentially everything you see in this image, except for the blue part in the middle and some of the red dots, is emission from pause. So they are ubiquitous in the interstellar medium of galaxies like the Milky Way and even lower mass galaxies. They produce these beautiful vibrational features that you can see here. This is the 3.3 that we were tracing with that 335 filter. And in fact, all of these different PA features can vary, and they tell you about the characteristics of the grains, which is fascinating. So you might wonder why we should care at all about PAs, and the reason is that they're very important for ISM physics. One of the most important things they do is they dominate the photoelectric heating of the interstellar medium. So this actually sets the temperature structure of the diffuse ISM, which is then what controls how much of that gas can get cold enough and dense enough to eventually become molecular clouds at some point. So PAs are really fundamental to ISM physics, and the degree to which they participate in this depends on their charge and size. So if a grain is highly charged, it's not likely to be able to eject more photoelectrons. So that impedes its efficiency. And like I mentioned, the spectrum of PHAs actually tell us about their properties. So here you see the different pH features and for neutral and ionized PHAs as a function of their size. And you might look at this and be like, oh, that seems complicated. And you'd be correct. There's a lot of features that are kind of varying as a function of charge and size. But one of them stands out, the 3.3 feature. This is from small neutral PHAs dominantly. And it is one of few things that's relatively unambiguous in that sense. So the ability of JWST to actually map 3.3 PHA emission is a new window we have into these dust grains, because previous telescopes, like Akari, for instance, could do it, but only for very bright objects. So with JWST, we can look at this for all of the dust in a galaxy. So we did this and developed a way to remove the continuum from starlight, which you see over here, from the 335 filter to look at the 3.3 PHA feature. And this was something I worked on. With that, we were able to look at the charge and size. And I'm going to go a little fast because I just want to mention that I'm going to talk about this tomorrow at Ralph's group meeting, and then also on Thursday at Galaxy Coffee at MPIA. So there will be a lot of other opportunities to discuss PHAs. But one thing I will just highlight is that what we found is that the abundance of these grains, the fraction of the dust that's made up of PHAs, drops dramatically in H2 regions. And Oleg, who's up here, who's a postdoc at ARI, was able to do the first test of how these grains are destroyed and found that their destruction, shown here, is correlated with the ionization parameter of the H2 region, which is something like the number of ionizing photons relative to the gas density. So this is actually one of the first direct constraints on how these things are destroyed. So I'm really excited about that result. So I'll just say that there's a lot more to come. And if you're interested, please join for one of these presentations. And I'm going to jump ahead to give you a brief summary of what we found in early science. So there are plenty of embedded star clusters. We've seen deeply embedded star formation. It seems to have a relatively short lifetime, something less than 2 megayears or so. There are filaments and bubbles everywhere in the ISM. We have various constraints on the behavior of PHAs. So they seem to be absent in H2 regions. And I didn't cover these, but we have the potential to use PHA emission as one of our highest resolution tracers we have of the interstellar medium in galaxies. So coming up next, there are only 3 more galaxies left to observe. And sometime relatively soon in the next year-ish, we will have a delivery of data products to MAST, which is the Archive for Space Telescope. And these early science results have really only just scratched the surface. I've already seen a lot of exciting things in preparation based on these data. They are also public, in case, I don't know, I always feel weird sort of advertising that, but all of this is public. And with that, I will leave you with one more beautiful image of a recent galaxy that has been observed. And thank you very much.
Thank you very much for this whirlwind tour. It was certainly mind-blowing. Gives us a great insight into what one might achieve. My imagination certainly was going wild during the talk.
I'm glad to hear that.
So would there be, I'm sure there will be questions also from the Zoom audience.
Yeah, this is amazing data and a very nice presentation. Thank you. I was wondering when you were talking about the central nuclear cluster, star cluster of one of these galaxies. I forgot the phone number.
68.
Right. And I was wondering, one of the explanations you mentioned was potential AGN activity but if you need gas for AGN activity.
Yeah, there's also
so it's a kind of chicken or egg problem, right?
Yeah, there's also no identified AGN there. Of course, there probably is a supermassive black hole, but
be a silent one, right? But still, if you say that for a couple of many giga years, nothing happened there in terms of gas, then
yeah, it's weird, huh? I mean, I agree. I think it's quite puzzling, like how there's this, void that, I mean, maybe it has to do with the fact that of, the galaxies we've looked at, NGC 628 really is a very perfect grand design spiral, if you ever want to pick out a very perfect grand design spiral. So perhaps it has to do with dynamical influences that prevent inflow into the center in some way, but I agree, it's really strange.
Okay, next question. So Saskia Hecker.
Thank you very much. Very interesting talk. I'm just intrigued by the bubbles.
Yeah.
I'm very much from another field. And I was wondering, is there any indication what they really are? I mean, you showed that there are the star forming regions or clusters at the edge, but what are the bubbles and how are they formed? Is there any indication of that?
Yeah. So I think my summary of this, and Liz, I don't think Liz is online, but at the moment, I think it's not clear how many of them are feedback driven versus dynamically driven. So just a void that's created by, whatever rotation of the galaxy. So we're working on a number of different ways to try to classify these and identify any populations that might be associated with that. But yeah, I think, the view of so many of these bubbles just was immediately striking and brings up a lot of questions, because this will be potentially an interesting tracer of feedback if most of them are feedback driven. And Liz has some really cool work, which I didn't show, about the size distribution of bubbles and whether or not that agrees with various theories of bubble formation, and if you have to have bubbles merging in order to explain the size distribution we've seen. So there are a lot of interesting questions there, and I don't have a lot of final answers at this point, but.
Okay, thank you. I don't at the moment see any hands up from the online audience. So let me ask a question. Sharon, this is an intriguing measurements that you've made, that there's a lot of CO, which basically is not associated with star formation in this galaxy. And I mean, not near to strong UV sources. And my question is there anything obvious, or have you looked yet at the velocity distribution in these CO clouds, clouds which are not near the star formation regions versus clouds which are near the star formation regions?
I mean, I think we may have the experts in the audience right now on that topic, people who have been looking at CO velocity dispersions near star forming regions. No? Okay. Well, so I'm not sure that the JWST results have gotten to anything new on the front of like whether there's young stellar populations associated with those clouds. Like I think maybe you're thinking of Ava's paper from.
Well, no. Well, I'm just thinking that there's probably, as you mentioned in your colloquium, there's probably gas traveling along these filamentary structures and then suddenly blowing up into stars. And then, before it actually gets to the place where it will eventually form the stars, it manages to stop itself through some mechanism for forming stars. So from that perspective, I was interested in whether there was anything different in the dynamics of those clouds compared to the clouds which had already started. I mean, I would expect that. Obviously, the star formation in the clouds is going to have an effect, but it will be interesting, since you can see first time these quiescent clouds, what the dynamical properties of those clouds were.
Yeah, that's a really good point. And I do think there are people looking into that on the team, but I am not sure. I know the latest, greatest results to report. I don't know if anyone who's in the audience does.
All right. Well, that's an interesting thing to ask you next time, maybe. And
it's a very interesting question.
I was interested in seeing how the PAR emission and the H2 regions are not quite co-spatial amongst others, what Oleg was working on. And I was wondering if we see the same effect when comparing the PAR emission with ALMA data, for example, for the molecular gas.
Yeah, so I sped through that really quick, but there is a really interesting result. So this was from a paper led by Adam Leroy. And what Adam found is that when you look at the PAH emission, about it actually in the fainter regions outside of the vicinity of star formation, it really resembles the CO. And in fact, there's an excellent correlation of gas and PAH emission in all of these galaxies. And in the vicinity of bright star forming regions, you can see, it's a little hard to see it here. Sorry, the projector is quite stretching it a bit, but there actually is a bright corresponding peak in the PAH emission. And the answer here is that about half of the PAH emission is tracing just gas throughout the galaxy, heated by the average interstellar radiation field. And about half of the PAH emission is coming from the vicinity of star forming regions where the radiation field is really intense. So it's actually a little bit of both, but yeah, your point is very insightful. And in fact, was a really interesting result, I think, of looking at these in great detail with JWST. So,
thank you very much. Returning back to your point about the dynamic scenario of bubble formation, can I think about this process as about a manifestation of dynamic instability, like in structure formation for galaxies in dark matter context, like growing genes instability, forming Zeldovich pancakes, turning into filaments, or is it something completely different for the gas, which is not collisionless, which has pressure, shock waves, interacts with radiation, and it is a completely different process comparing to the one in the galactic and comparing to the galactic structure and galaxy clusters?
I think that's a great question, and I wish I was the expert to answer it, but I think that it is the case that at least some of the bubbles are just places where, you know, perhaps the filaments have, you know, gotten denser, and so you can see the voids they've left around them, or that, you know, some kind of regularity of the rotation of the galaxy leads to forming kind of these filaments or spurs at a certain you know, spacing, like what in Sharon Might's paper was related to the turbulent genes length potentially. So my impression is that we have a lot of work ahead of us, and really interesting work, to try to understand the origin of the bubbles and how we distinguish between potential scenarios for, like, you know, whether they could be, some of the bubbles are like that sort of bubble, which I think they are, and then some of the bubbles are feedback driven bubbles. And it's probably going to involve some, you know, circularity, some like orientation relative to the spiral arms that lets you distinguish between those cases. And I think probably the person who you want to answer that is going to be Liz at her talk in May. But I also agree that this is a very interesting question. So thank you.
So it just remains for us to thank Karin again for this amazing talk. I mean, if there's any young astronomers who wanting something interesting to do, you could do a lot worse than dive into this JWST Treasury trove. And I think, Karin, that's your great service to us this afternoon, apart from your own insights, is to really tell us and make us all enthusiastic about these wonderful data sets. Thank you so much.